Hello friends, in our previous discussion we have covered most popular and widely used intra-AS routing protocol, that is RIP and OSPF. Now in this session we will cover the inter-AS routing protocol, that is Border Gateway Protocol, which is popularly known as BGP. After having covered the topics like overview of network layer, router architecture, forwarding and routing function of the router, IP4 and IP6 protocol, NAT and DHCP protocol, along with various routing algorithms and protocols like Dijkstra's link state algorithm, distance vector algorithm, OSPF, and RIP protocol. We are now reached to the fag end, that is the last topic from network layer, which is inter-AS protocol, typically Border Gateway Protocol BGP. In our earlier sessions, we have learned how ISPs, that is Internet Service Provider, uses RIP and OSPF to determine optimal path for source destination pair that are internal to same autonomous system AS. Let us now examine how paths are determined for source destination pairs that spans multiple autonomous systems. The Border Gateway Protocol version 4 is the de facto standard inter-AS routing protocol in today's internet. It is commonly referred to as BGP4 or simply BGP. Nevertheless, because BGP is an absolutely critical protocol for internet, in essence, it is the protocol that glues the whole thing together. As an inter-AS routing protocol, BGP provides each autonomous system a means to obtain subnet reachability information from neighboring autonomous system, propagate the reachability information to all routers internal to the autonomous system, and determine the good route to subnets based on the reachability information and on autonomous system policies. Most importantly, the BGP allows each subnet to advertise its existence to the rest of the internet. A subnet shouts like I exist and I am here, and the BGP makes sure that all the autonomous systems in the internet knows about the subnet and how to get there. If Border Gateway Protocol, that is BGP, would not have been there, then each subnet would be isolated and alone and unknown by the rest of the internet. Hence, BGP is the main source which enables the information to pass from one AS to other AS. Though the Border Gateway Protocol, that is BGP, is extremely complex, it is imperative to acquire at least the rudimentary understanding of how it works. In BGP, pair of routers exchange routing information over a semi-permanent TCP connection. The semi-permanent TCP connections for the network is shown here in the figure. Here there are three AS, that is autonomous system, AS1, AS2 and AS3. These are the three autonomous systems. And there are typically one such BGP TCP connection for each link that directly connects two router in two different AS. This is a typical TCP connection which connects two router in two different AS. There are four gateway routers, specifically 1C, 2A, 2C and 3A. Those establishing connections with router belong to other AS. These are the four gateway routers, and this is a TCP connection which enables inter-AS communication. Thus, there is a TCP connection between gateway routers 3A and 2C, and another connection 2A and 1C, as indicated by these red dashed lines. This typical line, which is indicated by a red dashed line, is an indication of eBGP connectivity. Here E stands for external, because we are talking about external link, external to the autonomous system. This particular link is used for external communication from, that is, one AS to another AS, that is inter AS communication is took place over eBGP. There are also semi-permanent BGP TCP connections between routers within an AS. That is one TCP connection for each pair of routers internal to an AS, creating a maze of TCP connections within each AS, as indicated by this blue dashed line. These particular links connecting the internal routers within an AS, these connecting links connecting the routers within an AS, these are the semi-permanent TCP connections which creates a mesh of TCP connections within the AS. Here the blue dashed line are the logical IBGP connectivity. I stands for internal to the AS, within an AS. E stands for external, I stands for internal. These are the eBGP connectivity, and these are within the AS. This is the IBGP connectivity. For each TCP connections, the two router at the end of connections are called as BGP peers. Any two pair of routers at the end of TCP connections, whether it is IBGP or eBGP, means here 2A and 1A and 1C and 1B are the BGP peers. Similarly, 1C and 2A are BGP peers. Similarly, 2C and 3A are BGP peers. 3A and 3B are BGP peers. 3B, 3C. Likewise, each pair of routers connected over either IBGP or eBGP termed as BGP peers. Furthermore, the TCP connection along with all the BGP message sent over the connection is called as BGP session. TCP connection along all BGP message communication between any pair of routers is nothing but the BGP session. The BGP session that spans two AS is called an external BGP session, that is eBGP session. Here these two nodes, suppose there is a communication between 1C and 2A, then that particular communication or session is termed as eBGP. And if there is a communication between two nodes within an AS, for example 1B and 1C, that will be termed as IBGP session. In this figure, the eBGP sessions were shown with red dashed lines and iBGP sessions were shown by blue dashed lines. Note that the BGP sessions line shown do not always correspond to the physical link. These are the notional representation. BGP allows each AS to learn which destinations are reachable via its neighboring AS. Now, we will see how BGP would distribute prefix reachability information or BGP sessions with the help of given figure. As you may expect, using eBGP sessions, that is external BGP sessions or these red dashed lines, between any gateway routers, either that is 1C or 2A or 2C or 3A. AS1 sends AS2 the list of prefix, that is X in our case. This is a prefix X. Here, this AS1 sends the list of prefix to AS2 for this eBGP session that are reachable from AS1. Whatever X prefix which are reachable through this AS1, that information is shared with another AS2 or eBGP session. And AS2 in turn sends AS1 through this path the list of prefix that are reachable from AS2. Here AS2 also sends message to AS1, that is a prefix reachability information which are reachable through this AS2. Means both AS1 as well as AS2 share their prefix reachability information with each other. Similarly, AS2 and AS3 also exchange prefix reachability information through their gateway router 2C and 3A. Which here both AS1 and AS2 share their information. Similarly, AS2 and AS3 share their information over these eBGP sessions through gateway routers. Also, when the gateway routers in any AS, that is autonomous system, receives an eBGP learned prefix, the gateway routers uses its iBGP sessions to distribute the prefix to the other routers in the AS. That is, on receipt of the prefix reachability information or gateway routers through eBGP session, this 2A gateway routers is then broadcast the same information to all the routers within an AS or iBGP sessions. Means the information which was received or eBGP will then distribute to all the routers within an AS or iBGP. Thus, all the routers in AS2 learn about the AS1 prefix, including the gateway router 2C. This 2A gateway router will flood the information to all the routers within the AS2. The gateway router 2C specifically in AS2 can therefore re-advertise AS1's prefix to AS3. On receipt of the updated information from 2A, this 2C, that is the gateway router, will then re-advertise the newly updated information to its counterpart in the AS3, that is to 3A or this eBGP session. When a router, either it may be gateway or the internal routers, learn about a new prefix, it creates an entry for that prefix in its own forwarding table. Thus, AS1 promises to AS2, it will forward datagrams towards X through AS1. That is AS1 X path. And AS2 in turn promises to AS3 that it will forward datagrams toward X through this AS3, AS2, AS1 X path. This is how the information is transferred within an that is inter and intra autonomous system. Having now a preliminary understanding of working of BGP, let us get a little deeper into it. In BGP, an autonomous system is identified by its globally unique autonomous system number, that is ASN. When a router advertises a prefix across BGP session, whether it is iBGP or eBGP, it includes with the prefix a number of BGP attributes. In BGP terminology, a prefix along with its attribute is called as root. The set of attribute is called as root. Thus, BGP peers advertises root to each other. Two of the most important attributes which constitutes the root is AS path, next is next hop. AS path, this attribute contains the autonomous systems through which the advertisements for the prefix has passed. When a prefix is passed into an AS, the AS adds its own ASN to the AS path attribute. Router uses this AS path attribute to detect and prevent looping advertisements. Specifically, if router sees that its AS is contained in the path list, it will reject the advertisement and hence avoid the looping. The next important attribute in the root is next hop, which provides the critical link between the inter and intra routing protocols. The next hop attribute has a subtle but important use. Next hop is the router interface that begins with AS path. The next hop attribute is used by the router to properly configure their forwarding tables. When a gateway router receives a route advertisement, it uses its import policy to decide whether to accept or filter the route or whether to set certain attributes such as router preference metrics. The import policy may filter a route because the autonomous system may not want to send traffic over one of the AS in the route's AS path. The gateway router may also filter a route because it already knows a preferable path. Now we will consider the two different scenarios of BGP path advertisements. Specifically, when gateway router have a single path to a destination and other gateway router has multiple paths to a destination. We will first see when the gateway router have only a single path to a destination. Here, AS3 autonomous system through gateway router 3A advertises the path AS3X to prefix X to one of the gateway router 2C in another autonomous system AS2 via eBGP. AS2 router on receipt of advertised route from AS3 or eBGP, that is on receipt of this advertisement from 3A, that is a gateway router belongs to AS3 or this eBGP session. This gateway router belongs to AS2 autonomous system. As per the policy of AS2, propagates this AS3X path to all its internal router or eBGP session or iBGP session internal to the router autonomous system 2. Latter, based on the AS2's routing policy, AS2's another gateway router, that is 2A, advertises the path AS2 AS3X, that is path to this prefix S, that is X AS3X, which is then add its own ASN, by then the path will be AS2 AS3X to the AS1's gateway router 1C or this eBGP link. The router 1C then propagates the same among all the intra-router or iBGP. On receipt of this path to this prefix X or this gateway router 1C, then 1C router will propagate this information all the internal routers using intra-routing policy or iBGP session. And thus AS2 promises AS1 a path towards prefix X through AS2. Hence, by passing this information, AS2 here promises to all the nodes or all the routers in AS1 a path to the route prefix X through AS2. This is a scenario when in this typical source AS1 is having the only one single path to the destination. Now we will see another scenario wherein we assume that there are multiple gateway router path to the destination. As seen in our earlier scenario, let us now assume that gateway router of the AS1, that is 1C, have two paths to destination prefix X. Here this 1C gateway router belongs to AS1 is having two paths to the prefix X. This is one path which we are already explored, and this is another path to the prefix X. As in case of our earlier scenario, Gateway router 3A advertises the path AS3X to its counterpart in AS2, that is 2C, and propagate the path AS3X to all its internal router, which are already seen, by using IBGP session. Here, this gateway router belongs to AS3, pass this AS3X path to its counterpart gateway router in AS2, and on receipt of the path from AS3, this gateway router 2C then propagates this path information to all its internal router for IBGP. Gateway router 2A from AS2 then propagates the AS3X and it's append its own AS2 information to another gateway router belongs to AS1. On this, that is on receipt of this AS3X path information, this gateway router 2A pass this AS3 to AS2, AS3 and X path information to its counterpart gateway router from AS1, that is 1C. But since the gateway router 1C from this autonomous system 1 has two paths to the destination, it has also received prefix X from 3A directly. It has received two prefixes there, one from 3A and one from 2A. Sorry. Based on the routing policy of AS1, minimum number of hops or least cost, etc. The gateway router 1C on receipt of two different paths from two different sources chooses or select one path and advertise the same within all its internal router via IBGP session. Here, typically in this example, 1C router will select this AS3X path over AS2, AS3X path based on the least number of hops, and it will advertise that this AS3X path to all its internal routers or IBGP session. This is a scenario when gateway router is having multiple paths to the destination. Here once is having multiple paths, this path and this another path. When based on the policy of AS1, this particular gateway router select the path which is having either less cost or less number of hops. In the next part of this session, we will discuss about how the forwarding table at the routers were updated when the gateway routers have multiple paths to the destination. Thank you. Thank you very much.